Hello everyone again. Welcome to our webinar this week. So far, we have had two webinars before, and this is the third one. My great pleasure this week, we have Professor Valerie Thomas from Georgia Institute of Technology. Professor Valerie Thomas is the Anderson Interface Professor of Natural Systems in the Milton Steward School of Industrial and System Engineering at the Georgia Institute of Technology. She also holds a joint appointment in the School of Public Policy. Thomas holds a PhD in the theoretical physics from Cornell University and is a graduate of Swarthmore College. She has previously worked at Carnegie Mellon University and Princeton University. She is a fellow of the IIS and the American Physical Society, and currently she is the treasurer of the International Society for Industrial Ecology. Today's presentation is titled Electricity Production Planning Methods for Sustainable Development Studies. Professor Valerie Thomas, the floor is open. Thank you so much for accepting our invitation again.
Thank you very much for having me. And now I will share my slides. This one. Okay, so I believe that I am sharing my starter slide. And so I'm going to be speaking today about this broad topic of electricity access and electricity infrastructure, electricity development in developing countries. I want to acknowledge that the photograph I'm showing here is one I have taken from the Stanford website from a publication of Marshall work. It shows the sky at night, or a simulation of the sky at night over Africa, and it shows that there are some regions that are very dark, especially if we compared this to what just to the north Europe would look like. In my talk today, I'm basically going to give a lot of background and sort of discussion around what the problem is, what would be the social problem, the technical problem that would be useful to be modeling. And even when I discuss the models, I'm going to discuss them rather conceptually. I show a few equations. The equations, for those who want it fully, are in the papers. And the people who are attending and interested in this seminar, I am somewhat assuming that maybe you are more from the optimization framework, which is the framework in which I and my group have been modeling. And there are some very different other frameworks, and I will mention them somewhat. And I also want to preface my remarks with an overarching comment that I notice in the area of electricity, even looking forward to more renewables, more, better use of storage, that kind of thing, there is a huge emphasis on modeling for developed countries and a lot of work on unit commitment and that kind of thing. And very little work for the situation of countries and regions that don't have much electric infrastructure. So the emphases are different. There are many approaches you can take, and I want to encourage people to work in this area. So this is something of an overview of what's out there. So one of the topics, one of the issues is that in many places, electricity access, as it's defined, is low. I'm going to be speaking today mostly about sub-Saharan Africa because that's the region for which I've been doing modeling. And as it happens, sub-Saharan Africa does include the region with the lowest electricity access overall. And generally, electricity access typically means something like residential electricity service. Sometimes it can mean that the town in which the person lives has residential electricity service. It may not mean that the actual residence has electricity. And it also may not mean that the person doesn't have access to electricity. I'll get into that in a minute. And for this overview portion, I'm using a lot of figures from the International Energy Agency's World Energy Outlook, WEO, expressed down here where you might not be able to see it, especially from a chapter in the 2019 World Energy Outlook called Africa Today. And so the numbers here in yellow are the population in millions, and the color refers to the share of population that lacks electricity access as defined by the International Energy Agency. So you see there's a lot of low access in this central portion of Africa. And the populations in, say, the Democratic Republic of Congo, notably, are quite large. Other countries have, especially Nigeria, is the largest economy in sub-Saharan Africa, and even there, the fraction of electricity, people without access to electricity is only about 50%. There are a couple of major goals. One is to provide 100% access to electricity to the entire population. And that has been modeled by the International Energy Agency in scenarios to try to reach 100% by, let's see if I can put this over here, by 2030. And you'll see this is for all of the areas without good electricity access. And you see that sub-Saharan Africa has lower access. And so getting to 100% access by 2030, which is part of the United Nations Sustainable Development Goals, requires that the increasing access line really ramp up its slope quite quickly, because now we're already in 2020. Another important goal is what is called access to clean cooking. In many developing countries, especially in sub-Saharan Africa, most of the cooking is done using biomass. That means wood, pieces of wood, that kind of thing, in indoor or outdoor open cooking. And the goal is clean cooking can mean a lot of things. It can mean improved cook stoves that are more efficient with using wood, and also have lower release of pollutants. And it can also mean propane cooking and electric cooking. So again, the goal is to reach 100% so-called clean cooking by 2030, which in sub-Saharan Africa would require that some kind of different thing starts happening now in order to somehow make this slope rise up substantially. One thing I think is very interesting is, oh dear, excuse me. Let me go back to this, which I think is the screen I'm still sharing, is that infrastructure development has not been the same in different areas of the world. That's not going to be surprising to anybody, but that infrastructure development of different types has developed differently. So this figure is showing the energy infrastructure in terms of megawatts of capacity of power generation, kind of, you know, basically how many power plants are there. This is telecommunications. And this one over here is transportation, with a very interesting metric of kilometers of paved road per kilometer squared of land area. This only is showing developing countries, again, sub-Saharan Africa way down here at a number that looks to me like about 0.01 kilometers of road per kilometer squared. Over here, take a look at the megawatts of power generation capacity per million people. The red line here is sub-Saharan Africa. Many of us here on the call are quantitative people, so let's look at the numbers. This is showing megawatts per million people, or similarly, watts of generation capacity per person. In sub-Saharan Africa, notice the line has it's not been going up, possibly been going down. The number is something like 150. 150 watts of capacity per person. This is much lower than the capacity in the United States, in developed countries, and it hasn't been going up. Now, look over here. This is interesting, is telecommunications. You can see in sub-Saharan Africa, as everywhere else, it's been going up a lot. And the number of fixed and mobile subscriptions per person is at, here is the axis for this line, about 0.8. And in sub-Saharan Africa, most of those subscriptions are mobile. It means that 0.8 of the people have, nearly 0.8, 0.75 here, about 3/4 of the people have a subscription to telecommunications, which I'll get to in a minute. Is very interesting because cell phones use electricity. Even though, as I said in the previous slide, most of the people don't have access to electricity. Okay, looking at infrastructure investments in the past in sub-Saharan Africa, over in the past decade, the majority of the investments in the energy infrastructure have been for petroleum. That is extraction of petroleum, most of which is exported, and also extraction of natural gas, most of which is exported. Those are the fossil fuel supply is shown in these red, purple, and gray bars, and the investment in the power system is shown in the yellow, green, and brown bars. And so this is showing investment in the electricity transmission and distribution network, low carbon power generation, and fossil fuel power generation. The number has been going up. The International Energy Agency projects much greater need for both to meet projected economic development goals. Now, I've been showing a few of these slides here from the International Energy Agency in their World Energy Outlook, as I said. What's shown here in the past, that's data. What's shown over here is models. How do they model this? The answer is they do not use least cost optimization models like many of us are used to doing, or that many of us are trained to work on. They use levelized cost of electricity models that choose for a given grid square the least cost generation in that square. So I'll get back to that a little bit at the very end, but I really want to highlight that these enormously influential global energy modeling systems are not optimization models. They are simulations, and they're not power system models. They are least cost models of meeting demand. So kind of interesting to realize that. The change in electricity access in sub-Saharan Africa has been relatively small, relatively slow. The population has been growing. And therefore, if the rate of increasing access is not as fast as the population is growing, the number of people with access to electricity could even go down. This slide, a little bit confusing to look at because the portion with access are shown here in the top. Those without access, so it has been going down a little bit, are mostly in, or about half in 5 countries: Nigeria, Democratic Republic of Congo, Ethiopia, Tanzania, and Uganda. These are large countries. So electrifying them will be something of a benchmark for the entire continent. And again, the change has been slow. A factor that I want to emphasize, especially because it's typically ignored, especially among those of us who do electricity system modeling, is that most of the energy used in sub-Saharan Africa, excepting South Africa, is biomass. It's like wood, and it's used for cooking. That is most of the energy. You see here the units are for the continent as a whole in million tons of oil equivalent, about 500. And so this green bar here is bioenergy. That does not mean something fancy like biofuel from Fischer-Tropsch processes. No, that means little chips of wood used in the house to do cooking, and sometimes charcoal. Other renewables are way over here in this tiny slot, so it's very small. And then there's a substantial amount of petroleum, that's oil, mostly used in transportation. So much of the modeling, including all of the technical modeling that I have done, has been focused on the electricity sector and improving that. And I just want to point out a tremendous opportunity, which is to consider the energy used for cooking. Not only because gathering biomass may have, it's awkward, it's time consuming for people. Perhaps more importantly, when people are burning wood or charcoal inside their houses, the health impacts are significant. And even nowadays, when people are moving from the countryside to urban areas, they continue to cook with either wood or more commonly charcoal inside their apartments in the cities, which can have very large impacts on urban air quality and most importantly on indoor air quality. And this is an area that has received a lot of attention in terms of efforts to make cleaner fuel stoves and distribute them, but very little in terms of the electricity modeling. Moreover, in terms of policy for electricity provision in these countries, the modeling and demand, the demand projections include expecting that people will continue to cook with biomass. So electricity supply is being built without enough electricity supply to cook the food. In particular, the amount of electricity, the amount of power needed to cook is typically around a kilowatt. You can verify this yourself by looking at the power rating on, say, your toaster oven, or you can do calculations of solar output and so on. It takes around a kilowatt. If you're especially efficient, maybe you can use 500 watts. And the electricity being provided, especially in rural areas, is not sufficient for that kind of cooking. So just putting it out there as a tremendous research opportunity to change the conversation by doing some research to show what it would take. to provide cooking electricity in sub-Saharan Africa. Another major issue is that the electricity supply is not highly reliable. Well, the consequences of this. One consequence of this is the electricity frequently goes out in many countries. This is showing the fraction of the total outages concentrated in Nigeria, mainly because Nigeria is the largest economy in sub-Saharan Africa. And it shows that there's 20 terawatt hours. I believe this is from 2016. It could be a few years earlier, of lost power. And it shows that backup generation is used both, in industry, in the service sector, and in residential sector. And that's an additional cost that people bear. Most of this backup generation is from relatively small diesel generators that more wealthy people will have on their properties. So, figuring out how to deal with electricity outages is another important area of research. And that can include how to make the electric grid more reliable. It can also include how to use backup generation or other approaches to overcome the fact that the electric grid is unreliable. This one is a few years ago, before I understood it, was very surprising to me. The topic of this slide is that there is an oversupply of power in East Africa. So that's the opposite of what I've been saying for the past 20 minutes. And so I see that it was Claire Nelson at Power Africa. Mistyped this here. Even though many people do not have residential access to electricity, and even though the economies of many of these sub-Saharan countries are underdeveloped and have potential for industrial and commercial growth, which would require more power. What has happened is that more power has been supplied, power plants have been being built and are continuing to be built, and demand has not risen to meet the supply sufficiently quickly. And the result of that is really quite terrible. The result of that is that the finances of the power utilities is, largely speaking, and to exaggerate, terrible in sub-Saharan Africa. And so one contributing factor is that in most countries, the regulators seek to have the lowest possible prices for electricity because people are not rich. Businesses are not wealthy. They need low-cost power in order to simply move forward. And that means that there's very little profit to start with. And then if there's not enough demand for the power that the utilities have to sell, their revenues are just too low. And so there's been constant problems with that. So specifically to show what is on this chart, it shows, I think this was made in 2017. And it's from Claire Nelson, who was working for Power Africa. That is part of the U.S. Agency for International Development, AID, and is an agency whose mission is to support U.S. industries in supplying power to Africa. And what it shows here is the the peak demand, which of course is higher, and this is projected into the future, the day demand and the night demand, which are lower, and they're projected to increase. The interesting thing is that in 2019, 2020, 2021, the power available at peak is higher than even peak demand by quite a good bit. And these projections, that means imaginations, but projections of future demand are that it will, in fact, increase. The y-axis here, excuse me, is in megawatts. This is a plot for Rwanda, and the total aspirational supply is some 550 megawatts for the whole country. And the expectation is that peak demand will reach that by something like 2030. So there's a huge problem in the current next 5 years and perhaps 10 years that there's more supply than demand. So this means for us in the modeling community that we need to be careful of not simply modeling what's the least cost way to provide more power, which I think would be a kind of natural setup of the problem. And in fact, it's work that I've done because the challenge is not only there's no power supply, there's not enough power supply, but also that there's not enough power demand. And so modeling how to increase demand is arguably perhaps more important than modeling how to increase supply. And in fact, in Rwanda, which is the country I know best, their policy is to no longer support construction of new supply of electricity unless it is also that part of the package is supplying the demand. That is, for a company that projects, proposes to build a new hydropower, it's a country with excellent hydropower resources. The company must also supply that demand, for example, by ensuring that, say, a local industrial facility can be accepting that new demand. So I am emphasizing this because it's often not what people are thinking is the requirement. And it's bamboozled people to understand, why this is happening, why there isn't more supply, because the watts per person is really low. Okay, so there are both standard types of power plants that those of us in developed countries are used to, natural gas combined cycle, and coal-fired power plants, even hydro plants, and increasingly in both developed countries and developing countries, there are standalone systems, and I'm highlighting here photovoltaic, PV. For those in the audience who may not be familiar with that abbreviation, photovoltaic, and they're called often solar home systems to emphasize it's a small system that might go on the roof of a house, such as here. There are two boys here putting up a solar system on what appears to be possibly their house, or perhaps they are contractors and putting it up on somebody else's house. And then diesel generators, as I also mentioned, are another option for non-grid electric technologies. Diesel generators are dominant in some ways. So the solar home systems, an issue there is that they are capital intensive. Using data from the South African power pool developed by IRENA, Energy Agency, which is a UN agency, Their modeling for the South African power pool is that a rural installed photovoltaic system with a 2-hour battery costs $4 a watt for approximately a 1 kilowatt system. I checked that out today. B-Box is a outstanding leading company supplying solar home systems in sub-Saharan Africa and other developing countries. Their system has a suggested retail price of $400. That system would supply either 15 watts, yes, that would be the entire system for the house, or a maximum of 50 watts. That's their large system. So I divided 400 by 50, that's $8 per watt. So even the cost of some of these systems exceed what are accepted as typical costs of $4 per watt. So we can compare that both with an off-grid diesel system, which according again to the National Renewable Energy Association is 70 cents per watt for a 1 kilowatt rural diesel generator. Of course, that does not include the fuel. Or for a connected system, like a utility scale photovoltaic system, the cost is about $1.50 per watt. And for comparison, a natural gas combined cycle power plant cost, again, that would be a grid-based system, is even less expensive than utility photovoltaics. That has a what's called an overnight cost of about $1 per watt. Of course, the natural gas combined natural gas combined cycle power plant, you need the fuel as well as you do for the generator, whereas the PV, you pay almost all of the costs up front. Okay, so here's what a system might look like. My student and colleague, Todd Levin, who now works at Argonne National Laboratory, was in northern Ghana in 2012. Northern Ghana is the rural part of the country, which is less electrified. So here we have a solar home system. It looks like about 50 watts, maybe 100 watts to me on the roof of a house. And you see a nice house here. And for interest, here is a goat. Inside the house, it would look, in fact, did look exactly like this. So here is the battery. It's a car battery, and that is being charged by the PV system on the roof. And then you can charge things with it, like it looks like these are cell phones being charged here. And so that's a typical setup, and it's quite a few of these phones that and maybe it's other devices that the family has. And then this provides the capacity to do all the fun things that families do, like watch soccer, football on television. Notice the little guy here, he has exactly the same shirt that my son had at that age. Or use a, is this a VHS system? To watch movies and so on. So you can have both a television, and I don't think we're seeing lighting in this particular photograph, but you get lighting, some television, because what they had shown there was a 100 watt system, it looked like to me, which is a pretty large system. So again, getting to this issue of what people have access to, as I mentioned before, cell phone ownership is high. These are data from Kenya, Tanzania, and Uganda showing cell phone ownership. So this is not like what I showed before, which is subscriptions per person. This is ownership per person of the phones. It's more than 80% in Uganda, yet electricity access in these countries is much lower. People who own these cell phones do indeed not simply own them, they actually charge them and use them. And so cell phones can be charged at retail locations, as is shown here a charging location, which can be both off-grid or possibly on-grid. It can be diesel-powered or solar-powered. These are unsubsidized. The market for the telecoms is largely unsubsidized compared to the electricity market, and it's been doing quite well. So interesting to keep in mind. Okay, so considering then some of the modeling that we've been done is, how do you choose? Do you build a centralized system or you build a decentralized system? So we've set up the question like this. You can compare the cost of centralized generation, here's some power plants, plus the transmission and distribution system. And the question is, when is that cheaper than the decentralized generation system? And we've looked at different versions of this. Like another difference here is there's low greenhouse gas emissions from photovoltaics, whereas possibly high greenhouse gas emissions from this power plant, depending on whether it's a nuclear plant or a fossil fuel plant. Those can be taken into account in models with constraints in the usual way. So there are 4 factors that can determine which one you want to do. An important one is the electricity consumption level, because if you're building this kind of transmission system, that can work great if there's high consumption at the end of the transmission line. But if there's extremely low 10 watt per person capacity consumption, and if the number of people in the area is low, it just is really hard to make this break even. The cost of the transmission infrastructure obviously matters a lot. And then what matters is the cost difference between the centralized generation and the decentralized generation. Obviously, if the decentralized generation cost on a from a simply direct levelized cost basis, if this is less than or equal to the centralized generation cost, then you'll always go for decentralized because you don't have to pay for the transmission. And then what's important is the network length required to connect the new population. So again, how much of this do you have to go? So this is one thing that we've modeled. We've done this using a least cost network approach. And I'll try to speed up here because I see we're fairly far into the time. And this is one of our outputs for the country of Botswana. This one is our baseline set of calculations, and then we're showing 9 because the answer depends both on the transmission cost. Overnight cost here means ignoring the long time required for financing and debt repayment and that sort of thing. So just paying it all at once and making the calculation that way. So how much is the transmission cost per kilometer? And also how much more does the decentralized generation cost? And what this figure shows, takes about 20 minutes to look at it to understand it, is that for this central picture of Botswana, for example, in the western half of the country, the people can be served with decentralized electricity for consumption per person per year up to 10,000 kilowatt hours per year. This is a break-even analysis. So, and in fact, typical consumption of people in Botswana, even that are connected to the grid, is only a few hundred kilowatt hours per year. So this is the kind of result we see. I'm emphasizing this because it depends tremendously on how the cost of, say, photovoltaics will be evolving in the future, as well as things like the transmission cost, and it depends tremendously on how much people will be consuming. A different kind of approach, kind of the standard approach. What we do is our bread and butter modeling is we do production planning optimization models. And I've written this equation down here as a simplified version of what goes on, with the objective being to minimize the cost of meeting demand. So the capacities here are shown in as the C's here are the costs, the generation costs, the fixed cost of the generation, the variable cost of the generation, and the decision variables are how much capacity to build and how much generation to supply. So we've done this in a multi-period spatially explicit way as a linear optimization model, and we've done some others to show with some more detail. We've looked at, there's the centralized infrastructure cost and the decentralized infrastructure cost and the decentralized production cost. So you can find the least cost way to supply the demand with all of those variables in what may be for some of the audience kind of a standard approach. So showing this kind of model, we did a case study of Rwanda, and so what we end up doing, this whole shaded area is somewhat the shape of the country, and we've shown the least cost way to build the electric infrastructure. We took just 110 kilovolt transmission lines, which is typical, what's considered high voltage, and lower voltage down to 30 kilovolts, excuse me. And the places with dots are the nodes that are served most cost effectively in a decentralized way for a particular set of parameters and a particular node resolution here that we chose. We've done this at a bunch of different levels. I'm showing again this kind of box plot here, which shows that the answer depends strongly on how much the decentralized electricity generation costs per watt. And it also depends a lot on how much power people consume. The more power, the more beneficial it is to use decentralized power. This particular box shows, excuse me, the more power they consume, the more advantageous it is to produce centralized power. This box shows decentralized power, which you build the most of if there is somewhat higher demand and relatively low cost for the decentralized, which is obvious. Okay, there are different questions. For different questions, you will have different models. So one thing we've looked at is looking at the stochastic nature of these systems. That is, the power goes out. Not only does the power go out a lot, also the development budgets change. And so you could be partway through building your power plant and the budget gets cut off. And there can be other kinds of problems you have in the system. So a different objective is to minimize the quantity of unserved electricity demand in each period. So we minimize the difference between the actual demand and the consumption that is applied either in a centralized or decentralized way. And to look at this, we have combined simulation with linear programming to understand the impacts of disruption to generation facilities. Some areas are subject to terrorism and natural disasters, disruption to transmission facilities, disruption to the development budget, repairs that need to be done, and then we also include construction of new generation. And then there are also probabilistic parameters like the budget itself may go up and down, commodity prices may change dramatically, demand may not be what we thought, and the transmission loss may be much larger than anyone would believe. So We don't really have generalized results. I'm just showing you some scenarios that we've looked at in which we've looked at situations. Well, what if you in a country don't build anymore? You just are working with what you have, and we've compared what the served demand would be in the deterministic case, showing with a star, and with the stochastic case, showing here in the black dots, and the costs can be quite a bit larger because here we're taking into account the possibility of severe disruptions and the need for repair. Here we've looked at, in red, a country making a decision to build more grid, on-base centralized grid capacity, and versus deciding to build more decentralized solar home systems. We show, obviously, in the stochastic case in which we take into account bad things happening, the served demand is lower, but we also show, and we show that for the same spending, you get more served demand with a grid system than with the non-grid system, because the grid system is cheaper, but because of the stochastic nature of problems that arise, both outages and so on, the difference between the expectation and the stochastic reality is bigger when you build the centralized system because of budget interruptions as well as transmission interruptions than with the decentralized system. So that's an example of the kind of thing that you can do. And now I want to have this be my last slide, and I will then stop and let anybody ask questions who want, which is to show that this is modeling by of the kind that is used by the International Energy Agency. As I was saying before, they don't use optimization models, so they're not calculating the least cost in the way that those in our community are used to doing it. But they are doing geospatial modeling on a fairly fine scale. And the result is they can show the same kinds of different scenarios like we're looking at with optimization models over the whole continent. So here is an example showing tier 1, which means that electricity demand is very low, just basic lighting, to tier 5, which is somewhat higher lighting that would somewhat higher consumption, including possibly as high as having a refrigerator, and high oil price versus low oil price. And so in the higher demand case, there is more grid development, more mini grid development, and less standalone solar home systems, whereas over here there are more solar home systems being built because demand is so low. So I will end my formal remarks now. I thank you for your attention and interest, and I welcome comments. Either just later, you can send me emails or something like that, or right now if there happens to be time.
Thank you so much, Professor Valerie. This was excellent talk. I learned so much, very interesting information about Africa and all the centralized and decentralized approach. I was wondering how easy it was to get this data. Is this collaboration with Power Africa or something else?
Yes, the data question is an important one. First of all, the data are important because the answers depend on the data you put in. The answers depend, I think, much more on the data and assumptions of your model than the actual, veracity of the model. We have to really look hard for data. The International Renewable Energy Agency has some data. I spend a lot of time searching for data online from the national utilities. Rwanda happens to be pretty good, that if you are really diligent, you can find their data. And the World Bank is sponsoring a site for electricity and energy data, in which the community is invited to post their data, because finding data are difficult. So excellent question, and you just have to enjoy data.
Yes, you're right. Thank you. Does anyone else has a question?
Hey, Olivera, there's a comment on the chat box. You may want to mention that as well.
Yes, so there is a comment from Enoch Moyenga. It will be interesting to check the progress of solar home systems in Zambia. As a country, we have made considerable progress and continue to grow. Just a suggestion.
So I'm very pleased to hear that there's someone online who knows about, or maybe is in Zambia, and I am very interested in Zambia and have been looking at that a little bit. I'm working with a Zambian PhD student, Katundu Imasiku, who's attending the University of Rwanda. So any information that the questioner has about solar home systems in Zambia and so on, it's very interesting. I know that in Zambia, most of the grid power is used in the mining and refining industries, and there's still quite a few people that at least are classified as not having access. So thank you for the comment.
I've got a contribution also to make. This is Enoch again. Just following to what I'd suggested, I'm a PhD student in Sweden, but come from Zambia.
Sweden.
I've installed quite a number of solar home systems. And recently we installed a system where we are monitoring data. We've managed to get, I think, now up to 3 months. When we have maybe up to 6 months or 12 months, it would be interesting to see how we could apply your presentation to the data that we get. And then also, if there is need, I've got solar home systems installers in the field that I know that I can actually get data and information if that would be needed. So that's the suggestion that I...
Thank you. That is a terrific suggestion, and it's very interesting to know all kinds of things about how people are using power, whether the supply is useful, the size, the composition. So that's terrific. What the demand profile looks like. So that's great.
Hi, Professor Thomas. This is Henry again. Again, I also want to thank for the presentation. It's great information and also a great perspective of looking at the different parts of the world, how they develop and use electricity. I'm a power system engineer, so I'm really coming from the power grid perspective. We used to study US power grid or European power grid. They're already pretty mature, they've been existed for more than a century, right? So,
Nice.
So it's a totally different situation in some other parts of the world, like you mentioned, Africa, but also some parts in Asia probably still in the situation they need more access to electricity and so on. I do have a few questions.
Mm-hmm.
Maybe I just ask one and then I can follow up with emails. We can continue the conversation. So when you specific about your method of optimizing the electricity access, as you compare the centralized versus decentralized methods, did you consider the reliable supply in the formulation. Why say reliable supply means, say, if you have all decentralized system, you may not have 24/7 electricity. Say you have 2-hour storage with a solar home system, we can only get you 2 hours at the most. But then you will not have electricity for the most of the nights, right? So in that situation, so if you consider those factors, does that, or have you considered this? Or if not, how would those other, like a reliable supply aspect, change the equation and change the results?
Yes, this is a great question, and yes, we thought about this. And what I showed you there with the 2-hour supply, I showed that because that was from the International Renewable Energy Agency, and it had specifically the cost as defined that way. Most of these solar home systems, as the expert from Zambia can correct me, but they actually have more, a longer period of storage than 2 hours. The ones I'm familiar with are built to have supply for, say, 3 days worth, but still you're getting small amounts of power, and it's stored, so you can have power at night, but the demand profile is very different than what might be happening in facilities that are set up with grid power. So yes, and it gets hard to model this really well without having the problem get very large, you know, like the cost of the distribution network as opposed to the transmission network. So there's a real difference between the centralized provision and the decentralized provision.
Mm-hmm. Mm-hmm.
Yeah.
Okay. Thank you.
Maybe I can also
Yeah.
add up to that one. Basically, like in Zambia, we got 2 cases. Provision of solar home systems for people who are connected to the grid, but are impacted by load shedding. So with such, we don't over-dimension the storage because, you know, at some point, the grid will be there, they will use the grid. And then we've got those in rural areas because the access to electricity in Zambia is way below 22%. So such, you have got to have a bit of more storage because all the time they've got to rely on the installed solar home systems. But then also, if we look at the rural areas, most of them, it's for writing and charging of phones. Like one of your slides, you showed that basically most of the people own phones, and that's the immediate need. So you have a split in that. And then of late, more have been on the DC systems because with the USB charging, people can charge the phone. So for rural electrification, typical in the villages, more DC systems are being encouraged than having a converter, which makes it even cost effective for the people to pay for the electricity. Of course, there are other business models that are there that makes it affordable for the people. Yeah.
That's great. Thank you. I'm so glad you're on here today.
Yes, Professor Valerie, if it's not a problem, I know we are a little bit over time. There is one question in the chat, if I can read from George.
Mm-hmm.
Okay, so he says, industries which from bulk of the demand of power generated by national utilities are installing grid-tied solar systems and will result in lower demand for the national utilities. How will this affect the oversupply problem you have mentioned?
That's a great question. I don't know the answer. It may be different in different countries. I am familiar that with fairly large industrial sites like cement plants, for example, they will build their own power supply to make sure that they have it. But then, and then as the questioner, as George just said, it could also be grid power. So, I mean, excuse me, it could be photovoltaic power. So, I think it will play out differently in different cases. I feel positively about developing more kind of utility scale, large scale PV and putting it on the grid, but managing the demand is a super interesting and as yet unresolved problem.
Okay. Thank you so much. We are a little bit over time, so maybe if someone has a question, they can forward to me and then I can reach to you, Professor Valerie, if that is not a problem. I also have a few questions. As Henry said, I may contact you later. So far, we have had, around like 14-15 people during the webinar were attendees. So I think that was great. Thank you so much for finding a time to give this wonderful talk to our community. I enjoyed a lot. Very interesting topic, and thank you so much again.
Great, thank you very much.
Professor Thomas, I also want to add my thanks to you as well. I enjoyed your presentation, especially with the background music from the chirping birds from the, I guess, your home area. That's quite a pleasant place, like you know, you're living here. Yeah. So hopefully we can have more conversation later on.
Great, me too. Thank you very much.
Thank you. Have a great day.
Thanks.
Thank you everyone for attending, and thank you the most, Henry, as well.
Thank you. Bye-bye.
Bye-bye.
Bye.